So hi everyone. In the last video we have seen about the degradation of penicillin and beta-lactam antibiotics. Today we will see the structural activity relationship of beta-lactam antibiotics such as penicillin and all. Okay. So this is very important topic for the semester exam also, and sometimes in medicinal chemistry portion they will ask question in competitive exam which are related to pharmaceutical competitive exam. Okay. Very important topic. You have to remember all the points. So let's see. First of all, we'll see the structure of beta-lactam antibiotics. So in this beta-lactam antibiotics, first of all, we see the beta-lactam ring. Okay. In that beta-lactam ring, in that beta-lactam ring, you will see one thiazolidine structure is connected. That day also I mentioned the heterocyclic structure naming. So in that, see, this is the sulfur because of that thia. This is the nitrogen because of that aza. And how many membered ring? 5-membered ring. So all thiazole. Again, since it is saturated, so it is odine in the last. So thiazolidine, prefix, then stem, then suffix. Okay, you will see that video also in that account. Now we'll see the side atoms. What are the side chain present in that? First of all, you will see nitrogen. In that you will see connected carboxyl group, and then one I. What it is called? It is called S-ilemine group. Okay. Now we'll see in that one carboxylic acid will be also connected here, carboxylic acid group, and 2 methyl group present here. Okay. Numbering according to caste system, numbering will start from sulfur, and according to other methods, I told you 3 methods to tell. Yes. So in caste system, numbering will start from sulfur. In USP system, numbering will start from nitrogen. So we'll start from nitrogen 1, 2, 3, 4, 5, 6, and 7. Now the important thing is that we'll see the SAR, that is structural activity relationship. That means the chemical structure of the penicillin. And in that penicillin, what are the chemical side atoms are present, and what are the chemical side chains are present, and how these side chains will go and bind to the atom, so bind to the receptor inside the body, and it will show its pharmacological activity. And also which side chain is important for what activity, which side chain is important for the stability, which side chain is important for the activity also. These things are very important for the SAR. You have to remember everything. So before going to tell you the SAR, I will mention one very important point that you have to remember, that the penicillin structure is composed of 2 different cyclic structures. That is beta-lactam antibiotics, right? So in that, first you will see that is ring 1 or ring A. That A ring is beta-lactam ring. This one. This one is beta-lactam ring. This one. And this beta-lactam ring is again fused with thiazolidine ring. Thiazolidine ring means this one. Okay. So this penicillin is composed of 2 different cyclic structures. One is beta-lactam ring, another is thiazolidine ring. Okay. Now in the first position, presence of nitrogen is essential and it is must. You can't replace this nitrogen. So this nitrogen is very important because it is only the main reason of beta-lactam ring, right? So presence of thiazolidine ring is essential for the activity of beta-lactam antibiotics. Okay, you can't replace that. Number 2, in second position you will see carboxylic acid. This carboxylic acid group is also very important because it increases the lipophilicity, and when lipophilicity will increase, ultimately it will increase the bioavailability of the penicillin inside the body. First thing. Second thing, so let's write there, increase lipophilicity. Okay. Next, second point is that it is this penicillin will bind to penicillin binding protein present on the bacteria. Okay, and present on the cell wall of the bacteria. So this carboxylic acid group will help, or it is the main reason through which this penicillin will bind to the PBP. That is called binding to PBP, penicillin binding protein, present on the cell wall of bacteria. So this is the main reason. So you can change that carboxylic acid group. You can replace it with ester or alcohol, but it is not good. Once you will do that, lipophilicity will decrease. So once lipophilicity will decrease, you have studied in pharmacokinetics, absorption also decrease. When absorption decrease, bioavailability will decrease. Number 2, binding to PBP will decrease. That means that activity will totally decrease. Why? Because it will act mainly by binding to PBP. Okay. Number 3, it is increasing the decreasing the polarity and increasing the non-polarity. In that case only, because of that reason only, lipophilicity will increase. So you can't change this one. Once you will change this one, the stability will also decrease. And third point is that it increases the acid stability. It increases the acid stability. So when acid stability will increase, what will happen? You can take that orally. Okay. When you will take that orally, it will go to the stomach. In the stomach, acid is present, so acid stability will be better. In that case, that carboxylic acid group presence is must necessary. In third point, you will see two methyl group are present. So both the methyl group will be present on the either side of the plane. So when these are present on the either side of the plane, ultimately it will increase the stability. Okay, and you can replace this one. Both the methyl group are characteristic property of beta-lactam antibiotics. You will see in penicillin also, you will see it in cephalosporin also. Okay, next in fourth position you will see one sulfur present. And presence of sulfur is very important for the activity of beta-lactam antibiotics. But if this sulfur is oxidized and it is oxidized into sulfone, okay, or if you can replace this sulfur with methyl group or alkyl group or any other atoms, like oxygen is also by double bonded atom, so you can replace it with oxygen also, but ultimately it will decrease the stability, it will decrease the activity also. When you will replace it with only CH2 group, that is alkyl group, in that case only stability will increase. But if stability is increasing and activity is decreasing, then there is no value. So better to have little bit less stability but having more activity. So that's why presence of sulfur is very, very important at the fourth position. At fifth position, you will see one hydrogen present. Okay, so with respect to this sulfur, this hydrogen is alpha hydrogen. Presence of this alpha hydrogen is must necessary. Once you will replace this alpha hydrogen, the activity of the penicillin will totally decrease. In sixth position, this is the most important position, that is sixth position. In sixth position, presence of nitrogen and that carboxyl group is very important. It will increase the stability, mainly acid stability. Okay, and since this nitrogen is more electronegative, that is electron withdrawing group, it will act as electron withdrawing group, and adding the electron withdrawing group at sixth position will activate the cyclic chain, and when it will activate the cyclic chain, activity of the penicillin will be more. Okay, next important point you have to remember at the sixth. Okay, let me write that one. So in that nitrogen, carboxyl group are essential. Next thing, addition of electron withdrawing group, that is called EWG. On addition of electron withdrawing group, activity will increase, and also stability will also increase. That is called acid stability. Acid stability will also increase. Okay, one more very, very important point, that is the activity of beta-lactam ring or activity of beta-lactam antibiotics are unstable, or it is wasted or totally broken down by using one enzyme which is produced by bacteria, that is called penicillinase enzyme or beta-lactamase enzyme. That beta-lactamase enzyme, if the bacteria are producing beta-lactamase enzyme, and if we can add a bulky group on the sixth position, that is second class and third class antibiotics, you will see that second class and third class of antibiotics are beta-lactamase resistant antibiotic. Why? Because of the presence of bulky group at sixth position. So presence of or addition of bulky group. Why bulky group? I'll tell you later after 1 minute. Let me tell this one, seventh position. Presence of bulky group will decrease the beta-lactamase activity. Lactamase activity. And you can also write this presence or addition of bulky group will increase the resistance against beta-lactamase enzyme. Okay, this is very, very important point you have to remember. Next, at 7th position, double bond O. The presence of double bond O on carbon makes it carboxyl group, and the presence of this carboxyl group is essential and it is must necessary. Presence of nitrogen and presence of carboxyl group is must necessary. Why? Because of the presence of nitrogen and carboxyl group adjacent, it is called amide. And when the cyclic amide is present, the cyclic amide is called beta-lactam ring. That's why the existence of beta-lactam antibiotics in mainly due to the presence of this nitrogen and carboxyl group. That's why presence of carboxyl group and nitrogen are very, very important. Okay. Now I will tell you a very important point. The addition of bulky group. Now I'll tell you. Okay. So this is all about beta-lactamase and beta-lactam antibiotics. This is the SAR of beta-lactam antibiotics. You have to remember. Now I will tell you the activity of bulky group, how it is working, and how the addition of bulky group will decrease the activity of enzyme and increase the resistance against the beta-lactamase. See, when the beta-lactamase enzyme will come, it will act here as a scissor and it will cut this beta-lactam ring. When the beta-lactam ring will be cutted by the enzyme, the beta-lactam ring is now destroyed. So beta-lactam activity will also decrease. Why? Because it will not go and it will not fixed on the NAD and NAM. What is that? N-acetyl glucosamine and N-acetyl muriatic acid. That is present on the cell wall of the bacteria. Now what will happen? If we will add any long bulky group, then it will come and it will cover it like that. It will come and it will cover it like that. So when it will cover the beta-lactam ring, now this scissor cannot come from here and it cannot come and it will act on the beta-lactam ring, and when it cannot act on the beta-lactam ring, ultimately beta-lactam ring will be saved. So that's why addition of bulky group at 6th position is very, very important and it is present. You will see, you check once all the 2nd and 3rd class of antibiotics, you will see at the 6th position the bulky groups are attached. Okay, so this is the SAR of beta-lactam antibiotics. Keep studying hard and thank you so much.